In this video, I'm going to build a real-time clock circuit using an Arduino Uno and the DS1307 real-time clock chip. I'm going to display the clock in a 7-segment LED display. Both the DS1307 and the LED display are using the I2C serial protocol, so that makes actually building the circuit a little easier than it would be. You don't use near as many pins from the Arduino. Also have a push button that I can use to adjust the clock settings.
Okay, so these are the components that are going to make up the Arduino real-time clock circuit. Of course, first, this is an Arduino Uno. You could probably use most any Arduino as long as it can handle the I2C serial protocol. This is the DS1307 integrated circuit chip. It's a 8-pin chip. This is the Quartz Oscillator. There's 2 pins on there. This is a 38 kilohertz. I think it's like 38.7268 kilohertz oscillator. Optionally, you can use a 3-volt lithium battery. So this will let the chip continue to keep the current time value if you should lose power. And then this is just kind of a fancy button switch that I use to adjust the time. Right now I have it set up so you can only move the time forward. You could easily modify the program to either add a second switch to move the time back or something like that. So each click will adjust the time by a minute. Okay, then of course this is the 7-segment LED. This is an I2C LED, so it's really simple to use.
Okay, so this is the datasheet for the DS1307 real-time clock chip. Here on the left, they're showing a typical operating circuit. The one thing you should know is that if you're using an Arduino as the I2C bus, you don't need these to pull-up resistors because the Arduino pins have internal pull-up resistors, so you can ignore those. Also, if you're not using the square wave out, and you won't be for just a typical clock application, you don't need the pull-up resistor for that as well. So the pin configurations, there's the DS1307 is 8 pin dip. Pins 1 and 2 are for the quartz crystal. The quartz crystal oscillator does not have polarity, so you can put either pin in either 1 or 2. You can reverse them; it doesn't matter. The pin number 3 is for the optional lithium-ion battery. So if you lose power, the clock will continue to keep time. Pin 4 is the ground. Pin 5 is the I2C data bus pin. Pin 6 is the I2C clock pin. Pin 7, again, is the optional square wave out. I think you can use this real-time clock chip as a basic function generator. You can generate some square waves at specific frequencies, but to just keep time, you don't need that pin. You can leave that floating. And then pin 8 is the voltage VCC, and if you go to the second page, these are so for the supply voltage. Minimum is 4.5 volts, max is 5.5, typical is 5. So that's for our Arduino Uno, that's perfect because you can output 5 volts to supply power. If you do use a backup battery, the lithium-ion battery, the minimum voltage is 2 volts, typical is 3, max 3.5. So if you get just a kind of a standard 3-volt lithium-ion battery, you'll be fine. Okay, so this is a schematic of the electric circuit, and of course the Arduino is on top, and then below that is the breadboard containing the components. And on the far right of the breadboard is the push button switch, which is used to do the clock adjustment, and that's connected to pin 9 on the Arduino, IO pin 9, and it's pulled high with a 10 kilo ohm resistor. Then in the middle of the breadboard is the DS1307 chip, and pins 1 and 2 contain the 38 kilohertz crystal oscillator. Pin 3 is connected to the 3-volt lithium ion battery. Pin 4 is connected to ground. Pin 5 is one of the I2C data bus elements, and that is the data bus. Pin 6 is the other element of the I2C data bus, and that is the clock bus. Pin 7 is the square wave out. We're not using that, so that's not connected. It's just left floating. Pin 8 is the VCC, the voltage in, and that's connected to the 5-volt power rail, which is powered by the Arduino. Then below that is the 7-segment LED display, and as I said, that's also I2C, so that connects to A4 and A5 on the Arduino as well, and is also powered by the 5-volt power rails. And then on the far left is the 3-volt lithium ion battery, which, as I said before, connects to pin 3 on the DS1307, and also connects to common ground. Okay, so before we look at the source code, I want to talk just a little bit about the I2C serial protocol. And like I said before, the advantage of using this protocol is that you only use 2 Arduino pins, and you can handle multiple I2C devices because there's just the data pin and the clock pin. So, and the way that works is each device is going to have its own unique address. So when the Arduino talks to that device, it first sends out the address it wants to talk to read or write from, and then it sends out commands to do the read or writing. And for the DS1307, the address, this is the binary address, 1101000, which is 68 hexadecimal. So in the source code, we'll see in a few minutes, we're going to be using that address to talk to the DS1307. The 7-segment LED display, I think its address is 70 hexadecimal. So the addresses do have to be unique, but I think as long as they're unique, you can. There's really, I don't think, any limit to the number of devices you can have on that on those buses, as long as all the addresses are unique. Okay, so when you talk to the clock chip, the clock chip has really 8 addresses that you can use, and then it also has an additional 56 bytes, 56 addresses that you can use for anything you want. The first 8 are reserved for specific elements of the chip, and so at address 0, and each address is 1 byte long. So address 0 is going to contain the seconds value, and these are stored in what's called binary coded decimal. And so the way that works is like the ones column value is going to be stored in the first 4 bits, and then the tens column value is going to be stored in the bits 4, 5, and 6, in those 3 bits. And you do that so you can really just save space, because if you're going to write, the possible seconds values go from 0 to 59, so you would need, if you want to save that as text, for example, you would need 2 bytes, one for the tens value and one for the ones value. So you can compress it by storing it in binary coded decimal, and the source code will handle that for you. And then the excuse me, the 7th bit, the high order bit, is a flag that I believe that resets the clock we're not going to use that. So at address 0, we're really just using the first 7 bits to set the seconds. The same for address 1. That's going to control the minutes, and the bit 7 is not used for that address. The next address is going to be the hours. The same thing. It's a little different because for hours you can have either a 12-hour clock or 24-hour clock, and that's determined on how you set bit 6. So if bit 6 is set low, you're going to be using a 12-hour clock that's going to have AM PM values. If bit 6 is set high, you're going to be using the 24-hour clock. The address 3 is going to be the day of the week, so you only need 3 bits for that because the possible values are only 1 through 7. So for this circuit, I'm really only using hours, minutes, and seconds. I'm not using the day, date, month, or year, although I am reading and writing from it, but I'm not displaying it. So just wanted to make that clear. So yeah, the day is going to be at address 3. Address 4 is going to be the date, which is going to be basically the day of the month. Address 5 is going to be the month. Address 6 is going to be the year. And address 7 we're not going to use. This is the control register, and this is what controls the frequency of the value, the frequency value that comes out of the square wave out pin. And I may do another video on that, but we're not going to use it for this one. And so basically, like I said, when the Arduino is going to read and write from these addresses, and I'll show you how that works in the source code. Okay, so this is the Arduino source code. This is just the standard Arduino IDE editor. And at the top we have the standard includes, you'll need time.h. The DS1307 doesn't need that, but the Arduino does because of the way we're going to be setting the time. Wire.h, any I2C protocol devices are going to need this library. The next two you won't need unless you're using the same 7-segment LED display that I'm using. You could use, any kind of like standard LCD display to display the time. The one I'm using is the 7-segment LED Adafruit backpack, so that's why I have these two libraries. These next two addresses are the I2C addresses. First for the DS1307, which is 68 hex, and then the 7-segment LED display, the address is 70 hex. I have a couple constants here that I'll explain in a little bit. I declare the variable for the 7-segment display. It's called matrix. The input pin, that's going to be for the button switch to adjust the time. And I have a function that debounces that button, and this is just a delay parameter I'm using for that. And then the methods that are going to be called, so we have decimal to binary coded decimal and binary coded decimal to decimal. So these are going to be used when we read and write from the DS1307, because like I said before, that's how the data is stored there in binary coded decimal, so we have to have a way of converting back and forth. Okay, so this next function is how you set the date and time on the DS1307, set DS1307. You pass it in the variables for seconds, minutes, hours, day of week, day of month, in year. And then, like I said before, we're really only using hours and minutes for this clock, but this is going to go ahead and set everything. And so the way you set it using the wire library, you first want to begin transmission, and then you pass it the DS1307 address, which remember was hex 68. Then you want to tell it which address in the DS1307 you want to start writing to, and recall the seconds register. Seconds byte was at address 0, so we're going to pass that as 0, and then it's going to start writing, calling the decimal, the binary coded decimal, the seconds that were input, minutes, hours, week, day, month, and year. Now, it doesn't actually write on the buses when you call these right. It buffers those on the Arduino. And it doesn't really write anything until you actually call end transmission. That's when the write actually occurs. This also has, I'm also writing to the control register. Recall that controls the square wave output. We're not using that. I think I was doing some testing, trying to hook that up to an oscilloscope just so I could see how that worked. But you don't really need these lines. You can just omit those if you want to. Okay, then this next function is get date DS1307. So this retrieves the date from the chip. And again, you do a begin transmission. You send it the address, which is hex 68. Tell it which address on that chip you want to start reading from. That's going to be address 0, which again is the seconds. And when you do a read, then you do, since you have to write to tell it what address you want to start reading from, you do have to do an end transmission to force that write to occur. Okay, so then when you want to read, you're going to do wire.request from, and then again you give it hex 68, the I2C address, and then how many bytes you want to read. So it's going to start reading at address 0 and read 7 bytes. And remember, each address is 1 byte. So these are the 7 bytes it's going to read: seconds, minutes, hours, day of week, day of month, and year. And again, now you have to do binary coded decimal to decimal when you do the read. These little masks are, okay, so 7F hex is binary 1111111, which is 7 ones, 7 least significant bits. So that omits reading that first bit in that field. If you recall, that was a control bit. Only the first 7 bits of the seconds was used. And similarly, remember with the hours, some of those high order bits had to do with whether you were setting a 12 or 24 hour clock. So this is the first 6 least significant bits, or what you're masking when you read the hours. And then for C programmers, these are passed in as pointers. So when you set these, whatever called this function, these are going to be the new values that come out. Okay, so this next function, process sync message. This is a function that's called when you initially set the clock, and I'll show you how to do that after we go over the code. But basically, in the Arduino serial monitor, you type in the Unix time, and it will read that. It'll read that from the serial port and convert it to this PC time variable, and that is what gets returned. And its time t is the structure. So that's going to it's going to convert what you type in, which looks like just a bunch of numbers, and it's going to convert it into the hours, minutes, seconds, days, months, years. Okay, so this next function is debounce. So recall the button is for setting the time, and anytime you have a push button that you're trying to read from, it actually, what they call, it bounces. So it doesn't just go from on to off. It'll go on off on off on off really quick before it finally settles down to the end state. So debounce is a function that kind of lets you ignore all that off and on, and just kind of gets, one push, and then it'll get the final state. Okay, and this next function is just the standard Arduino setup functions that all the sketches have to have. And here's where you're going to want to do the wire begin. Remember, wire is the I2C library, and you have to do that and usually do it in setup to initialize it. Same for serial port. We're going to call begin 9600 baud. And then the 7-segment LED matrix, we're going to call begin for that. And it takes the I2C address as the input parameter, and that was 70 hex. We're going to set the pin mode for the input pin, which is pin 9, as input, and that pin is connected to the button that can adjust the clock. Okay, so this is the standard Arduino loop function. We're going to declare a bunch of byte variables that are going to contain the seconds, minutes, hours, day of week, day, month, in year. And this, okay, so this if clause, this isn't going to be called, you're not going to go in here very often. This is only called when you want to set the clock. So recall, when you set the clock initially, you do it through the Arduino serial monitor. So it checks to see if there's anything available to read in that serial monitor, and if it is, it's going to call that function we looked at earlier, process sync message, that returns the time t. So it receives the user input, converts it to this time t structure, and then the time t structure is used in this set time function. Now this is an Arduino function, so that's setting the time on the Arduino itself. It's not doing anything with the DS1307 chip. So you can set the time on the Arduino. The problem is if you ever lose power, the time is gone. It doesn't remember it. So we're going to set it initially here so that we can do an adjust time, because the time structure that's returned from process sync message is in GMT time, and I live in Central Time, so I have to do an adjustment, and it depends on if it's daylight savings time or not, what kind of adjustment I do. So subtract 6 hours to go from GMT to Central Time. So this is in seconds. So it's, is that right? Yeah. And then if it were daylight savings time, it would be 18,000 seconds. Okay, so then we're going to populate these variables from the Arduino time and then pass those in to set date DS1307. You could really skip, I think, setting the time on the Arduino, but this just had a nice way to convert that time t function. Once you set the time and adjust it, then you can use these functions to kind of pull those values out in that, because that's what is going to get passed in to set the parameters on the DS1307. Also, one thing, the DS1307, the year is actually a 2-digit year, so you have to subtract 2000 from it. So the DS1307, once 2100 rolls around, they're not going to work, or the current ones aren't, because they're not Y2100 compliant. And I think the leap year calculations stop working, according to the datasheet anyway, I think at 2100. So that's just something to be aware of. Okay, so recall this whole if clause was kind of when you initially set the DS1307. Then normally what's going to happen in this loop is you're just going to call get date DS1307, and that's going to return the current time values and date values. Okay, so, and like I said, we're really only concerned with hours and minutes. So I declared a variable called decimal time, and since the clock is going to be like a 4-digit display, the left 2 digits are going to represent the hour, and the right to the minutes. So to get the hours to the left, I'm going to multiply that by 100 and then add the minutes. Okay, then the matrix is the 7-segment display, and just call print, and it's going to print the decimal time. And this draw colon function, you pass it a boolean whether or not you want the colon displayed between the hours and minutes, and I do. And then you do right display, and that actually does the right. Okay, so then after the time is written, the code checks to see if the adjust button is being pressed. So it calls this debounce, like I explained before. Debounce will only, for a certain period of time, will ignore all the bouncing that the switch does, and then checks to see if the state is changed. So if the state is low, that means it's being pressed, so it's going to increment the minute by 1, and if that increment is greater than 60, it sets it to 0, and then it calls another set date, DS1307. So these other values haven't changed. So what's different is now it's passing in new minute. So new minute was this variable that got adjusted here. Then delay 200 microseconds. That you don't really need that, but it doesn't hurt anything. So anyway, that's pretty much it. The code's not that complicated. Like I said, you can use any kind of display. I like this Adafruit 7-segment display, but you could use just a standard LCD type display. Okay, so now I'm gonna set the clock. I've uploaded the script to the Arduino. So what you want to do is go to the serial monitor, and this is just some debug I have printing out for the button switch debounce function, so you can just ignore that. So to set it, you're going to start with the letter T for like set time, I guess, and then we're going to go to this site called www.epochconverter.com, because the time you have to use through the serial monitor is called this Unix epoch time, and that's in GMT. So you just want to copy that value and paste it in here. Just hit enter, and then that sets the time. So I just adjusted my clock from daylight savings time just to Central Standard Time. So there you have it. It's not really too difficult to build this and put this circuit together. Pretty basic, really. If you have any questions, leave them in the comments. Thanks for watching.